How many grams of each of the following reagents are required to prepare 250 milliliters of a 1.10 molar solution? So in this problem, all three are going to be done exactly the same way. It's just a different chemical. So as you'll see, the molar mass is going to be different, but the procedure is going to be the same. The key in understanding how to do this problem right here is that molarity is a conversion factor that we're going to use to convert between the given volume of solution that we want to prepare and our answer of how many grams. So going from volume of solution to grams of solute, conversion factor is going to be the molarity. Let's generalize on that. When we're looking at a 1.10 molar solution, as in this problem, this is the same as saying we have 1.10 moles of the solute, and the solute is going to be the chemical in question. In this case, we have three different chemicals that are going to be the solutes per 1 liter of solution. We're given a volume in milliliters, and we're going to be able to convert that to liters, therefore have the proper units for the denominator. Our moles of solute, we know that 1.10 using the molar mass is going to give us our desired grams. So we can go ahead and start. Let's first get the molar mass of sodium fluoride. That first of all has a formula of Na3P, and then looking up the atomic weights and doing the math, we get a value of 99.94 grams per mole. We'll get the molar masses for the other two as we go along. So let's start this problem then, and let's represent it with the letter A, so we'll keep track of our three different chemicals. Our measurement given was 250 milliliters. I'm going to write that in ordinary notation. Let's remember that we have three significant figures on that number. Our answer, of course, is going to be in grams. Our first conversion factor then is going to be converting our milliliters to liters. We have 1 liter over 1,000 milliliters. Milliliters cancel. I now have liters, and now I can use my conversion factor, molarity, and I'm going to use as is. I'm going to have moles upstairs, liters downstairs, because I want liters to cancel. So I've got 1.10 moles upstairs per 1 liter. My liters cancel. I now have moles. To get grams, we use the molar mass, 99.94 grams per mole. Moles cancel. So we now have the proper units, and we can do the calculation, and we get a value of 27.5 grams. Three significant figures in our answer as determined by our starting measurement. The only other, well, we have three significant figures here in our molarity as well. We have four significant figures here in our molar mass. Let's move on to part B. In part B, we're looking at the number of grams needed to make a 1.10 molar solution of ammonium chloride. So our part B, ammonium chloride has the formula NH4Cl. The molar mass of ammonium chloride is 53.49 grams per mole. Our procedure is going to be exactly the same. Our conversion factor, same setup, milliliters to liters, and then moles to grams from our conversion factor. So we start again with 250 milliliters of our solution times 1 liter over 1,000 milliliters. Milliliters again cancel. Now I use my conversion factor, molarity, 1.10 moles per liter. Liters cancel. And now the molar mass to convert to grams, 53.49 grams per mole. Moles cancel. And I'm going to be left with grams, which is my desired unit. Doing the math, we get a value of 14.7 grams of ammonium chloride needs to be weighed out, dissolved in 250 milliliters to give us our desired 1.10 molar solution. Our last chemical is going to be part C, and here we're looking at an aqueous solution of potassium oxalate. Now you may need to look that formula up. Oxalate is not one of the common ions that we talked about with our nomenclature, but the chemical formula is K2C2O4. So the oxalate anion is a polyatomic anion, C2O4, with a -2 charge. What we need here is the molar mass of this salt, and that turns out to be 166.22. Again, please verify that with the atomic weights from the periodic table. Setup is exactly the same because, again, we're making up a 250 milliliter solution to a same concentration of 1.10 molar. So again, we start with 250 milliliters. We're going to convert that to liters, 1 liter over 1,000 milliliters. Then we're going to use our molarity conversion factor of 1.10 moles of potassium oxalate per liter. And then using the molar mass, we're going to convert that moles to grams, 166.22 grams of potassium oxalate in 1 mole. So moles cancel. We have grams again as before, nothing new there, 45.7 grams of potassium oxalate is required to make up this solution to the desired concentration.